So Lights Out is a game where you turn lights on and off. Anyways, we'll play a little bit. So last time we talked about spanning things, and we took a look at possibly a span of two vectors in R2 might span the whole plane, and we kind of talked about what that meant. You guys know what I'm talking about when we talked about that stuff? Let's see. No. Let's take a look at the lecture from last time and see if we can try to recover some of that stuff in our memories. Yeah, if we have two vectors. So in our last example, we wanted to know if V was in a span of U1 and U2. And so we found out that it was in fact in the span by letting some constants x equal to -5 and y equal to +3. And if we did that, that linear combination of U and V would, U1 and U2, the linear combination of U1 and U2 would get us V. So we took that a step further and went on to say that, in fact, this V was almost arbitrary. If we could have let that be any vector or any point on R2, if we let that to be any point in R2, then we can somehow get to that point by a linear combination of U1 and U2. So it turns out that if you're able to do that, we didn't answer this, or we answered it in class, but I didn't write it down for some reason. If you were able to let any point, if you were able to let V be any point in R2, then these two vectors would eventually get to that point. Then we have to say that the span of U1 and U2 can be anything in R2. Okay, so that's the last thing that we kind of mentioned. So I don't know if that makes any sense, but let's see if we can try to recover this. So we talked about this from last time, and what we did here is we let V be any point, and it turns out that we can eventually get to that point by U1 and U2. And so the answer to this question, what is a span of U1 and U2, you can get any point V in R2 as a linear combination of U1 and U2. And because you can get to any point in R2, we can say that the span of U1 and U2 is all of R2. Okay? That means if I pick any point in R2, my two vectors, U1 and U2, can get to that point by just doing scalar multiplication and addition. Okay? All right. So there's some theory behind that, and this is the whole idea of spanning and spanning sets and stuff leads to the idea of linear independence. So before we focus and talk more about linear independence, let's just do another example that they have in the book and talking about the span of things. So how do we show that something is a span of R3, for example? So let's do number 11. And if we want to do this, we want to pick a vector from R3. Now, we can pick an actual vector, a specific vector, or we can pick a general vector. And the general vector can be x, y, z. So let's let x, y, z be a vector in R3. And this symbol over here, the sideways z, looks like an epsilon. It says it means it's an element of. Is an element of. So this vector is an element of R3. And what we want to know is that can we find three constants, alpha and beta and gamma. I guess I could have used x, y, and z, but I'll use alpha, I'll use Greek letters. So can we find three vectors such that alpha times 1, 0, 1 plus beta times 1, 1, 0 plus gamma times 0, 1, 1, and let that equal to x, y, and z. No, this looks like another system. It just looks like a system of linear equations we should be able to solve. So I'll multiply this across. We got alpha plus beta plus 0 is equal to x. We got 0 times alpha, 1 beta plus gamma is equal to y. And then alpha plus gamma is equal to z. And if we put this in a matrix form, alpha, beta, 0, x, 0, beta, gamma, y, alpha, 0, oh, wait. I'm looking at the coefficients here. So sorry about that. So wherever there's an alpha or beta, let's just put 1 and then zeros everywhere else. And then I think if we just row echelon form by getting rid of that last one down in the bottom. So we could do that by taking R1, multiplying it by -1, and adding it to R3. Oh, we have to do one more. So z minus x And then, yeah. The whole left row, this one? I'm not going to be able to get rid of this one.
If you just subtract row 3 from row 1.
And then this would be a 0, but then row 3 would still have a 1. So there's no elementary row operations that would make one whole column equal to 0 unless that variable wasn't there. All right, so let's just do one more step over here, and that is to just add row 2 and row 3 and replace row 3. So this would be z minus x plus y. So not quite row echelon, or not quite reduced, not reduced row echelon, but it's in row echelon form. And then we can find the solutions for gamma, and then for beta, and then for alpha eventually. So there are solutions for this. So we can say that it looks like the 3 vectors So it looks like the 3 vectors actually span all of R3. Because if I pick any random point that I want, I could just find my alpha and beta and gamma that would get me to that point. Okay. So I suppose we should do one where it's not going to span everything. So let's make up an example where it's not going to span everything. Are we good with this? All right, let's do an example where it's not going to span everything. Example, span of, I need 3 vectors. 1, 1, 0, 0, 1, 1, and 0, 1, 0. Okay, let's see if this spans all of R3. Question? Does it span all of R3? So let's set it up the same way, and we'll see that when we talk about linear independence, there's a slightly simpler way to approach this. But we'll begin the same way. Let's let x, y, z be an element of R3. And then, so can we find alpha and beta and gamma so that this is equal to x, y, z. All right, so our system of linear equations is just going to be alpha plus 0 beta plus gamma, 0 gamma. Wait, is that right? No, is equal to x. So alpha is equal to x. Alpha plus beta plus gamma is equal to y, and beta plus gamma. Nope, just beta. Oh, wait. I think this actually spans about all of our three. Sorry, let me change the problem a little bit. Make it easy for myself. 1, 2, 1. I'm going to change the last vector as 1, 2, 1. Okay. So I think my system looks okay now. Okay. So now I just take the coefficients. 1, 0, 1, and then the x. 1, 1, 2, and then the y. 0, 1, 1, and then the z. Okay. So I suppose our first step should be taking this, getting rid of this guy. So we need to take our first row, multiply that by -1, add it to row 2, replace row 2. So this first row doesn't change. The second row, this one becomes 0. This remains the same. -1, so this becomes +1. And this becomes y minus x. Didn't change the last row, so let's leave it as that. Now, if I go on to the next step, which is to get rid of this 1 over here, I'm going to take my row 2, multiply that by -1 again, and add it to row 3. And what happens next is that the whole left-hand side disappears, right? And then this, whatever happens here is whatever happens here is z minus y plus x or whatever. But now we have this whole row over here of zeros. And so what we're saying here is that I can't randomly pick any point x, y, z in R3. I can only pick combinations of x, y, z where this equation is equal to 0, where this equation is satisfied. What can you tell? Yeah, Daniel?
The first one you did, wasn't it very similar separate type?
Yeah, it was the one that we did right before this one was this, but it looks like we can solve for 2 gamma is equal to this thing, and then we can find any point that we want.
So it's only equals to 0,
Yeah, if you get a whole row of zeros when you do the row reducing, then you don't span those 3 dimensions. Yeah.
Do we have to bother with the x, y, z's on the right?
Well, we'll see in one of the theorems that you won't have to bother with that to find out if it's linearly independent. Yeah. Nick?
What about the columns?
The columns?
If you have zeros in the column.
If you have zeros in the columns, then that's not going to affect this so much. No, actually, if you have zeros in the columns, then there's probably going to be zeros in the rows too. It's one of the other theorems. What?
Would this be
So it doesn't span. So it doesn't span all of R3. What is this? Anybody know what this is? An arrow. It's what? The amount of solutions? Close. Even more than just a smooth surface. No? A plane. Okay. This is a plane in R3. It turns out that this plane in R3 is a span. This plane is the span of those three vectors that we had, whatever they were. 1, 1, 0, 0, 1, 1, 1, 2, 1. So you have three vectors, and they span a plane. Can you imagine how this thing looks like geometrically? It's in R3, so we can still visualize it. Let's visualize it. I feel like I'm spending a little too much time on this. So let me draw the vectors. Let's draw this in yellow and make it kind of transparent. And I'm going to draw three vectors from the origin. The first vector is 1, 1, 0, was it? So what can you tell me about that particular vector that was drawn? It's what? It's on the plane, right? Now, can you guess what's up with the other three vectors if we were to draw the other three vectors? Would it be perpendicular? It would be, all three vectors should be on the plane. Because anything that you add, subtract, multiply. Uh-oh. What was the radius again? 5? And the other vector is 0, 1, 1. So these two vectors actually should be on the plane because any linear combination of these two vectors will keep you on that plane. Now, if we draw the third vector, and what was the third vector? 1, 2, 1. It turns out that that third vector is also on the plane. So between the three vectors, I can't get myself out of that plane. I'm kind of stuck on that plane. And so I can't span any other point outside of that plane. So here, we're only stuck on the plane. Okay. Okay. So this is a good lead-in to our definition of linear independence. So we'll see if we can come back to this picture again. Yeah. Where they're pointing isn't really that important. If I put a negative in front of one of them, They may or may not be pointing in the y direction, but the point is that they're still on the plane. All three of them are on the plane. So if I look at it carefully, it looks like, yeah, they're kind of pointing in the positive y direction, but I think that's irrelevant. All right, let's take a look at the definition that we're trying to get at, and that's linear independence. And the way linear independence sometimes is defined is kind of different from different books. But this is how they define it in your book. A set of vectors v1 through vk is linearly dependent. So they talk about dependent first. If there are scalars c1 through ck, that's our alpha, beta, gamma, where at least one of them is not 0, such that this thing is equal to 0. So that's a weird definition. And to further complicate that, the linear independence is when it's not linearly dependent. Okay, well, we will use this definition. This definition is kind of mentioned in a roundabout way, but we saw those three vectors in R3 that were on the plane. So it turns out that our three vectors, 1, 1, 0, 0, 1, 1, and 1, 2, 1. So these vectors, the set is linearly what? Dependent. It's linearly dependent, and so by definition, we should be able to find C1 times 1, 1, 0 plus C2 times 0, 1, 1 plus C3 times 1, 2, 1 equal to 0. So can you give me constants that I can put in this box to make this equal to 0? Except not all zeros. Three, -2, -1. Is that going to amount to that? No. 1, 1, -1. So 1, 0, -1, so that's 0. 1 plus 1 is 2, minus 2 is 0. 1, that's 0, and this is 1, minus 1. 1 minus 1 is 0. So we found non-zero numbers, not all of them are 0, such that this worked out. Okay? So the other example we had, you remember what the other example was? 101, 110, and 011. Is that right? Independent. Oh, whatever. So this is independent. So the question for you is, can I find three numbers that's not equal to 0 so that this would be equal to 0? So we can make some guesses. We can throw some guesses out there. But what we can do instead is to, well, what if we make a system out of this, right? Shall we make a system out of this? Let's call it C1, C2, C3. So this would be C1 plus C2 plus 0, C3. Now this, by the way, I was being a little sloppy here. This is a 0 vector. According to the definition, the 0 here is a vector, which means it has components. So that's the first component is 0. Our second part of our system is 0 times C1, C2 plus C3 equal to 0. And our third part of our system is C1 plus C2 is 0, C3. Right? That's our system. And let's put this in augmented form, augmented matrix form. And you start thinking, hey, this is kind of like deja vu, right? Because a couple of slides ago, we did the same thing, except we had X, Y, and Z. This is the same matrix as we're dealing with, except we had X, Y, Z instead of 0, 0, 0. So the point is, we can eventually get this to look like this in row echelon form, right? And then from here, we can then rewrite this as C1 plus C2 equal to 0, C2 plus C3 equal to 0, C3 equal to 0, and when C3 is equal to 0, you back solve. C2 is equal to what? C2 is also equal to 0, and when C2 is equal to 0, you back solve. C1 is equal to what? C1 is equal to 0. So the only possible solution you have there is when all C1 and C2 and C3 are all equal to 0. The only way you can get this to equal to 0, so that's why it's independent. By definition, this says that we can find C1, C2, C3, not all of them equal to 0, then it would be dependent. So the converse of that, if you can't find, if the only C1, C2, C3 here is forced to be 0, 0, 0, then by definition it has to be independent. So it turns out this is going to be our way to check linear independence. Okay? Any questions? There's probably a lot of questions. Huh? All right, I'm just going to breeze through a couple more theorems here, and then we'll check on the applications. First theorem, if you have vectors that are linearly dependent, then at least one of them can be expressed as a combination of the others. So example, we had that one linearly independent example, right? 1, 1, 0, and 0, 1, 1. I'm going to write it a little bit apart here. And 1, 2, 1. Remember these three vectors were linearly dependent? It turns out that the way I got this, I tried to do a fancy one, but then it turned out to be independent. So in my head, what I did was I just added the first two vectors to get my third vector. And so all this is saying is that the third vector is a linear combination of the other two vectors. So if you have something that's dependent, then you could do this for at least one of the vectors. Hell, you could do it for all of them. If I move this around, a 0, 1, 1 is also a linear combination of the other two vectors, right? Just by -1 or whatever. So that's what that is. That's what that theorem is saying. Let's take a look at the next theorem. Let V1 through Vm be column vectors of Rn. Then the matrix made out of those vectors as columns is going to be an important matrix for us to deal with. So it turns out that if they're linearly dependent, if and only if the homogeneous augmented matrix has a non-trivial solution. What? Again, let's take a look at our example. And I'm not going to rewrite everything. In fact, I'm just going to kind of sick of rewriting that example. Let's take a look at our dependent set of matrices of vectors here. Did you notice the matrix that was associated with this? I suppose I should copy it also. Is this it? This is it, right? And change the x, y, and z into 0, 0, 0. Did you guys notice this as I was doing it? Look at the vectors and look at the matrix. Right? It's not a coincidence that the vectors actually turn out to be the column vectors of the matrix. And if I go ahead and put 0, 0, 0 here to look at the non-trivial form, do you remember what we got when we row reduced this? Yeah. And if the x, y, z were all equal to 0, we'll just put zeros over there. We had a whole row of zeros, right? What does that mean? We have a non-trivial solution. That means, what this means is that if we back solve, or if we solve for this, the rest of this, we have C1 plus C3 equal to 0, and we have C2 plus C3 equal to 0. And because we have a whole row of zeros there, we have to let one of them equal to a parameter. Let's let C3 equal to a parameter. then C2 is equal to negative t, right? Negative C2 is equal to negative C3, which is equal to t, and then C1 is equal to, also equal to negative t. Right? So if that's the case, then I have a whole bunch of answers. It looks like there's no constant coefficients, so I just have 1, negative 1, negative 1. So if I let t equal to 1, C3 is equal to, oh, I got it backwards. Yeah, I wrote C3 first. Okay, so now that I have this, I can let t equal to anything, right? Then I have a linear combination over there. So, did we talk about trivial solutions and non-trivial solutions? What's a trivial solution? So a trivial solution is zeros, 0, 0, 0. That's a trivial solution. A non-trivial solution is a solution that's not 0, 0, 0. Okay? So when we talk about a trivial solution, that means 0 vector is the only solution. Yeah? So I got it from here. Once we let C3 equal to t, then I went to C2 plus t is equal to 0, and then I solve for C2. And then same thing for the first equation. Well, at this point, this says that I can choose any t that I want, and then that's going to give me a solution. Okay? A non-trivial solution just means you get a solution that's non-zero. At least one non-zero. At least one non-zero solution. Okay, so we found at least one non-zero solution. In fact, we found an infinite number of non-zero solutions by letting t equal to anything. Okay, so you see where this is going? So this phrase over here, if and only if, means that the opposite is going to hold true. What does that mean? Well, that means linearly independent if and only if the augmented has only the trivial solution. Okay, so let me take this theorem again and rephrase this part over here. So V1 through Vm are linearly independent if and only if, IFF is short for if and only if, the augmented matrix has only a trivial solution. All right? So we actually did this already, right? Just to make it clear where this comes from, let's take a look at our linearly independent example. And the result from that so these are linearly independent. If you notice that they're exactly the column vectors for that original matrix, the augmented matrix. And then we row reduced it, and we got this. And then if you remember, we ended up saying C3 is equal to 0. And so C2 plus C3 is equal to 0. But since C3 is equal to 0, C2 is also equal to 0. And C1 is also equal to 0. So the only possible solution we had was 0, 0, 0. This is a trivial solution. And because we only got the trivial solution here, that must mean that this thing, the original vectors that we were dealing with, are linearly independent. Okay? So basically, if you can row reduce and keep all the columns here, no 0 rows, then you have independent vectors. If you're to row reduce and then you come up with a row of zeros, then those vectors must be dependent. All right? Any questions? Okay. And I think this is the last theorem here. Is it the last theorem? So this is a little trickier. It's not as natural as the other one, but here what you could do is you can make your vectors into row vectors. If you make them into row vectors and then you row reduce them and you count the number of non-zero rows you have left, then remember the rank is the number of non-zero row vectors after reducing. If the rank is less than m, the number of vectors you have total, you've essentially gotten rid of one of them as a linear combination of the others. And so that must mean that they're linearly dependent. So just to remind you, the rank of A is the number of non-zero rows after row reducing. Okay? All right. Well, I think you have some homework problems that deal with this kind of stuff, so you guys can work it out. Are we good? You guys don't look happy. What? I know it's Monday, but you got two people nodding every time I say, is that okay? Two people nod, everybody else just kind of, yeah. So I don't know if it's okay or not. I'm going by two people in this class. And it may or may not be a good thing. Nick. Uh-huh. Less than the number of rows. Yeah. Yeah. It's what? If you have a row of zeros, that means it's dependent. Yeah. Dependent. Yeah, it's kind of like that. So when your rank isn't the full thing, essentially when your rank isn't the full thing, then you're going to have linearly dependent vectors. Dependent. So easy to say independent and dependent. Easy to mix them up. All right, looks like I have some problems here. I don't know if we should do any of them. Determine if they're linearly independent or dependent. Which one should we do? You know what? I'm going to use Wolfram Alpha. Did you guys get your second worksheet yet? Oh. I had a second worksheet ready for you guys. Let's see if it's online. Well, while I'm waiting for this thing to load, it's not here. Your second worksheet will be using FreeMat or MATLAB to row reduce matrices. So, sorry I haven't put it up yet. I'll put it up today. It's a good question. Probably after the test. The test is a week from today, yeah. Probably in Wednesday next week. Yeah, Daniel. Oh, yeah, eventually. I hope to get it to you before the end of the semester. It took a long time to grade them. I was talking to somebody about automating it so that you just submit it online and then you automatically get a grade. I haven't gotten around to that, so sorry. Okay. Yeah, I'm going to use Wolfram Alpha. And so let's do one of these problems. Number 28 looks like it's a 4-dimensional vector. Let's get that set up and see what happens. Let's do number 28. And we want to check for linear independence. So we want to see if these vectors are linearly independent from each other. And the way to get this set up, or one way to get this set up, there's a bunch of theorems that we just saw, right? We can take a look at the rank theorem, or you can take a look at the theorem where we just set this up as column vectors. And so let's do that. Let's do the first one where we set this up as column vectors. So 1, 2, 3, 4, 3, 2, 3, 4, 2, 0, 5, 4. And you really don't need these zeros. You really don't need the augmented part, because if you could just row reduce this into something where you don't have zeros in the bottom, then you're all good. But you can put the zeros if you want. I think it's good, just good practice to have that in the beginning. All right, let's take a look at Mr. Wolfram here. And see what he has to say. We're going to row reduce the matrix 1, 2, 3, 0, 4, 3, 2, 0, 3, 4, 2, 0, and 0, 5, 4, 0. So if you row reduce this, we see that we got a whole bottom full of zeros here. Oh, wait a minute. Huh. It's a bottom full of zeros, but I don't think we have any free variables here. This is a little tricky. Should have thought about this a little bit better. So this is the reduced row echelon form. And we were looking for non-trivial solutions, right? So the question is, do we have non-trivial solutions? If we throw this back into a matrix, into our solution set, our system, C1 times this, C2 times that, C3 times the last vector. We're solving for C1, C2, C3. And if we throw this back into the system, we would have C1 is equal to 0, C2 is equal to 0, and C3 is equal to 0. So it looks like we only have a trivial solution. So we only have the trivial solution here. What does that mean? Is it independent or dependent? It's independent. So the vectors are independent, turns out. Now that's, you know, we talked about a whole row of zeros. We got a row of zeros here, right? That row of zeros really has nothing to do with the solutions that we're getting. It turns out that we have a whole row of zeros because the vectors come from R4. And then we're looking for 3 coefficients. So we've been dealing with square matrices, so 3 by 3 matrices. But when it becomes not 3 by 3 anymore, then it gets a little trickier. So vectors are independent by, I don't think I labeled the theorems, by one of those theorems. Now, if we were to take a look at this as row vectors and then try to find the rank, then that should give us the same result, that it's independent, which means the rank should equal to the number of vectors. So let's take a look at that particular theorem. Now, let's consider this, instead of columns, as rows. 1, 4, 3, 0, 2, 3, 4, 5, 3, 2, 2, 4. Okay? Let's row reduce this to find the rank. By saying let's row reduce this, I mean let's have Wolfram row reduce it. So 3 vectors are 1, 1, 4, 3, 0, 2, 3, 4, 5. 3, 2, 2, 4. And so this is what it looks like row reduced, which means what's the rank? Rank is how many non-zero vectors, right? Or how many non-zero rows? So there's 3 non-zero rows, and then it turns out the rank of A equals number of vectors. It's not less, it's actually equal to the number of vectors, and then that was denoted as M in the theorem. M is a number of vectors. So here, we didn't lose a vector by doing the row reduction, and so we come up with the same conclusion. Vectors are still going to be independent. Yeah? For this theorem, this is that last theorem that was presented, yeah. And then so the vectors actually have to be denoted as rows. So when you say you have to, according to that theorem, you have to. But later on, we'll see that the rank of this as a column vector versus row vectors are going to be the same, right? If we row reduce this, we see 3 columns or 3 rows, also non-zero rows. So it's not a coincidence that the rank is the same. But according to that theorem, yeah. All right, any questions? All right, the next topic, falling behind again, the next topic are applications. And so what I'm going to do is I'm going to show you one application, that game, and then I'll put a link online for you guys to mess around with it and try to see how well you do. And it's a game called Lights Out. So the game, this particular game is written in Python using this environment called Code Sculptor. And when you open that link, you'll see this. I haven't found a way to make it a standalone application, so you have to actually run the program. So you can click on this arrow to run it. and then this thing pops up. The idea is to, when you click on a light, that light turns on, and then the other two lights next to it also turn on. And when you click on the light that's already on, that light turns off, and then the other two lights next to it also turns off. And so the key is to make all the lights turn off. Okay? So here I won. So for this one, you have to turn off, you have to click a certain combination of these lights to see if you can get them all to turn off. Okay? So it turns out that there's a nice way to do this with vectors and linear independence. Because if you think about the lights being on and off as ones and zeros, then those are just those vectors. So that's one variation of the game. Another, or that's one version of the game. Another variation of the game is to have the lights turn on. I didn't know what else to do, so I just colored it in. When you click on a light that's off, it'll turn on yellow. And when you click on the light that's yellow, it'll turn to red. And then when you click on it again, it'll turn back to off. So instead of just having on and off now, there's three states. A state that it's off, a state that it's kind of on, and then a state that it's really on. And so the question is, with the same objective, can you get this all to turn off? So this is a little bit more challenging. For those, somebody said that they played Lights Out before? Was it like this? The actual Lights Out game is actually a two-dimensional grid. So I'll show you that version next time. Oh, cube. Oh, that's even trickier. All right, we got a lot to do. I'll put the review online sometime between tonight and tomorrow, so that we can have something to review on Wednesday.